Hello Physics Nation, my name is Nate Larmond and this is video 3 on height and walking pace. I, went to the dialog, so I'm going to try to do my file sharing in the little orange and blue dialog bubbles. So go to here, and the Google form creates a spreadsheet. I grabbed the hyperlink to that spreadsheet, and then we pasted it into our own spreadsheet. Had to clean up some formatting issues, and we produced this graph. So, this graph tells a story. That was the point of watching the Gapminder video, How to End Extreme Poverty. Professor Rosling can tell a story with data, and this is a skill we're going to practice over and over again. Once you can figure out the story and sort of describe it with a mathematical model, you can predict outcomes like, given a height, tell me this walking pace. Doesn't seem that interesting, a physical system right now, but let's say you were designing Disneyland and your clients were 5 years old. So what's their walking pace? What's a reasonable time to go from this end of the park to that end of the park? Or a public transit system, or a high school. If you give students 3 minutes in between classes and the average high school kid walks at this walking pace, is 3 minutes sufficient? You can actually find all sorts of practical applications to use mathematical models to predict outcomes and sort of evaluate systems. And that's the game we're going to play, except our graphical display has all sorts of issues. And in fact, our spreadsheet has all sorts of issues. Hang on, let me do the halo. Never, ever have an untitled spreadsheet. So that's my bad. I forgot to name my file. Let's call it height and walking pace demo fall 2020. I'm going to put my name in the file heading. I think that's best practice. Okay, I now have a title for my file, and this graph is a little bit messed up. So, like I said, Google automatically sometimes will choose correctly. It put the independent on the X with the correct label, put the dependent on the Y with the correct label, and we're halfway there with this graph. Let me turn off the halo. All right, so let's click on the graph and hit the little 3 dots. We're going to edit this chart. So setup, it chose correctly. That was miraculous. Here we're going to have to change a little bit. In series, I want a trend line. And a linear trend line is fine. I think a label, I'd like the equation as the label. All right, so let's now compress series again. The way you do this is you can choose setup and expand each one of these, and then customize and expand each one of these. So we're almost there. We have our trend line, and we have the model, y equals mx plus b up here. I know the font's small. Maybe I should bump up the font. How do I do that? 14? Whoops, no, that's for the dots. Well, maybe under legend is legend font size. So I want it big. Yes, there we go. So under legend, let's make this legend font even bigger. There you go. Y equals mx plus b. So let's get this halo. There's the slope, 0.0142. What does that slope mean? And a y-intercept of negative 1.33. What does that mean? So I know you've done a million slope calculations, and I know you've done a million intercept calculations, but in science class, these have physical significance. So slope, these labels are really small too. I wonder if I could bump up the font for the chart and axis titles. Let's see. Chart title, yeah, horizontal axis title. So font size, no, I don't want auto. I want, boom, 20 looks great. And then we go to vertical axis title, auto, no, let's do 20 over here. Okay, so that's much better. Now you can read pace is our dependent variable, or y as they say in math class, and height is our independent variable. So slope, I know you've done change in y over change in x. So it's the change in pace per 1 unit change in height. That is, how many meters per second change for every 1 centimeter change in height? So, not that much change, 0.0142. But what if we multiplied by 100? Well, that would be 1.42 change in meters per second for every 1 meter change in height. All right, so it takes a little bit of practice, but again, just say change in y divided by change in x, and then replace y with this, change in pace per 1 unit change in height. And we're going to play that game where we just change math language into science language over and over again. Okay, so let's deal with this y-intercept. Let's play this game again. They say it's the value of y when x equals 0. So they substitute in 0 right here for x, and this term drops out. And they say when height is 0, when x is 0, pace is negative 1.33 meters per second. So there are limits to fitting a linear model to experimental data. When your height is 0, you have a walking pace of negative 1.33 meters per second. Like, I don't even know what that means. So, apply a linear model, but maybe, well, it's hard to really see the pattern in this experimental data because there's another problem. Let me turn the halo off. Our scale doesn't start from 0. And, different teachers will tell you different things, but the origin, a height of 0 and a walking pace of 0, may have an interesting sort of physical significance. So how do you change the scale axis? I think you come on down to horizontal axis, and we're going to make the minimum 0. So it certainly does change the look of this graph. Let's make the max a little bit different too. 200 centimeters is the maximum right here. Let's make it, I don't know, how about 240? Yeah, so this is a little bit more interesting because now it's not really the y-intercept that's interesting. The y would intercept down here. That's the negative 1.33 meters per second. What's interesting to me is the x-intercept. See, left of this point, there is no walking pace. It doesn't make sense. A negative walking pace, I don't know, you're like walking backwards. It doesn't have any real physical meaning. But to the right of this x-intercept does have a physical meaning. This is suggesting after about, I don't even know, 90 centimeters of height, you start walking at a faster and faster pace as your height increases. So this x-intercept does actually predict the height at which you begin to be able to walk. I don't know if that's accurate or not, but this is just one of the many tricks we're going to use. Hansel Rosling is a genius. He was trying to use data visualizations to prove that you may be 50 years behind the way you think of extreme poverty in the world. And I don't know what the class's hypothesis was concerning the relationship between height and walking pace, but this looks like Ariana's data set, right? This appears to show that the taller people do indeed walk at a faster walking pace, and the x-intercept suggests the height just under 1 meter, just under 100 centimeters, at which humans begin to first be able to walk. So, interesting mathematical model. Is it valid? Is it truthful? Who knows? We only did a sample size here of, I don't know, like 40, 37, 38 students. Not really big enough to figure out broad patterns. Anyway, that's enough for video number 3. Thanks for watching. See you in the next video.